SPDM stands for Simulation Process and Data Management. Today's webinar is organized by me, my colleague at Kaserakar, and my colleague Alex Dukin, who will conduct the live demo part of the webinar. And to introduce our company, ESTECO is the largest independent software provider focused on numerical optimization and simulation data management. And our technology consists of two key technologies: our desktop framework called ModeFrontier and our web platform VOLTA, and that will be the focus of today's talk. So quickly introducing ModeFrontier. This is our desktop client meant for process integration, automation, design optimization, design of experiments, robust design and reliability, and data analytics and visualization. VOLTA, on the other hand, is our server-based framework, and we'll cover some really good aspects of that today, which is a framework meant for sharing, collaboration, running multidisciplinary design projects on the web using a server-based approach, versioning, controlling your data, and connecting from it anytime, anywhere from a mobile device. So very quickly, what are the benefits from an MDO running it on the server compared to a traditional desktop application? So first, let's introduce the concept of optimization. When we are designing an aircraft, for example, we have to deal with a lot of competing objectives and requirements. On one hand, we would like, for example, an airfoil that generates a lot of lift, but at the same time, we want it to have a very low drag. We want an engine to be powerful with a lot of thrust. At the same time, we want to have a low fuel consumptions and low emissions, and so on and so on. So a lot of these objectives and requirements compete with each other. So how do you make sure that you select the best compromise? So this is where optimization, or better, multidisciplinary design optimization comes in. Now, for example, traditionally, when we are looking at a desktop application, we see typically the approach where the individual domain experts, they are working on their expertise. For example, you have a structural person who's working on the wing structure. You have the aero guy who's doing the CFD analysis. You have the propulsion being done mostly by the tier 1 vendor, and so on and so on. Now, and all these individual experts are working on their individual models, but at some point, these have to come together in a framework to glue these domains together and conduct system optimization. And this is traditionally done on a desktop. Now, to give an example how that would run in practice, and this is also one of the examples we will show in the live demo later. Here we have a very simplified wing structure where we're using a code called OpenVSP for the wing arrow and a code called ANSYS for the wing structure. You can see what the inputs are, what the objectives are, and what the constraints are. And in the little animated video, you can see some of the design configurations that the algorithm might explore. Now, when we are doing a desktop application, you might see something like this. This workflow was created in ModeFrontier, but the philosophy of all commercially available desktop frameworks is very similar. You define the inputs, which feed into a model. You extract the outputs, and those outputs might feed into the next solver as an input. And at some point, you identify the constraints and objectives. You pick an algorithm, and the solver will take care of the rest for you. So this could, for example, be an aero guy working on his wing model using OpenVSP. And the structural guy is kind of following the same approach, but he's using a different code, different inputs to develop, in this case, a very simplified wing spar, where the objective is to minimize the mass and to minimize the deflection. And as you can imagine, these are competing objectives. Now, at some point, these two persons have to start collaborating. And on a desktop framework, collaborating is difficult because there's only one place for a person behind the computer at the time. But you might see something like this when these two individual domain workflows are glued together. Now we have the two disciplines in the MDO workflow with the desktop approach. And as you can see, some of the limitations become visible very quickly. This is a very simplified problem, but if you have a, let's say, a real industrial application with dozens, maybe hundreds of inputs, and maybe 5 to 10 solvers, many outputs, constraints, you can see that with an approach like this, you can quickly end up with a one big messy workflow. Another disadvantage is that we are relying on an MDO expert to collect and connect all the individual domain models. And usually that gets done by having some sort of a shared file drive or emailing files back and forth. And with that, you have very little security. There's also no clear ownership, no version control. If someone changes, if the domain expert makes a change to his domain model, you can only hope that that change gets communicated to the MDO person, but he might never know for sure whether he is really using the up-to-date information. By having to build one of these big workflows all at once, it also becomes more difficult to debug because you have to go through many steps. And if somewhere in the workflow there is a connection made wrong, it might be hard to identify where exactly that is. On the execution side, most desktop tools, they can submit to HPC clusters or clouds, but typically you'll see limited capability and flexibility regarding distributed execution. And since this really relies on one expert gluing everything together, it becomes kind of hard to collaborate among team members and to live up to the M in MDO. Now, if we take that same example with a server-based approach, now we can manage each of these individual domain workflows and call them from a server. So in this case, where you see these round icons, they represent a workflow. Here the workflow for the wing arrow, and here the workflow for the structure. And you can right away see that this is a much cleaner way of representing the overall MDO workflow. And the nice thing is that in the case of VOLTA, each of these individual nodes is a version controlled workflow with managed ownership, sharing and permissions. And each of these nodes can be submitted to a specific queue of computers. So one part of the workflow can be submitted to an HPC framework, or the next part of the framework, of the workflow can be submitted to your own laptop if it's a fast running model. So it's highly flexible from a distributed execution perspective. Plus, you're always using the latest version from the subject matter expert. So a little bit more on the technology itself. With VOLTA, we can safeguard all the data, set the permissions, so the different participants in the project can only do what the system allows it to do, whether that's viewing, running, or full control. So in that sense, you also protect your company's IP. With the version control, you can track the changes and capture the engineering knowledge. The MDO really becomes institutionalized instead of an expert-only application. And VOLTA doesn't only version control the files that are related to Mode Frontier or VOLTA, but any sort of file that you wanted to manage, it can. So support files, images, simulation files, etc. We just spoke about the desktop, the limitations in distributed execution on a desktop, but here you can see with VOLTA how we can reduce the lead time by smart using all the compute resources we have. So we can submit parts of the workflow to a cloud, parts of a workflow to HPC or to your own working station. So you can really execute simulations in parallel and exploit the multi-core workstations. If you have external apps that you would like to communicate with it, that's possible too through the APIs. And finally, another nice aspect is that all the visualization and decision making is done online. So you don't have to do a screen dump and put that in a PowerPoint and send it to your manager. And then he might ask, well, what if we change this? And then you have to go back again, redo the analysis, make a new image. You can all do this online in a very collaborative way. So you can pick a designs, apply the filter, and the next person who logs in, who you wanted to see, he sees the same results with the same filters applied. So it's a very nice way to stimulate collaboration and decision making. So to summarize the benefits of VOLTA before we go into the demo, it really helps managing big MDO workflows discipline by discipline, which also makes it much easier to debug. There is security, ownership, and version control. You can always trace back who created the file or who created the workflow, who made changes to it, latest version, etc. And by doing so, we really see that has been a need identified by the industry that MDO is typically an expert-only application. There's one person who collects all these models and tries to connect them all together. But at the same time, many different people in an organization can benefit from optimization. So by using a server-based approach, we can really scale up MDO across the organization and institutionalize it. And by doing so, that of course stimulates collaboration and breaking down silos. As we just saw, we have high flexibility regarding distributed execution. And very appropriate for this time, everybody's working from home. So it is also very nice if you can access your MDO framework 24/7 from any location and run optimization even from your iPad. And also not unimportant is that we have a lightweight IT installation available. Typically, when you go to a server-based approach, many people might be reluctant and thinking that this is going to be a huge burden on IT. But in case of VOLTA, this has been shown to be very lightweight, easy to deploy. This can be up and running in a matter of 2-3 hours. You don't need days or weeks to deploy this. So I would like to end my part. I forgot to mention, if you have questions, you can type them into the Q&A box and we will address them the last 5 to 10 minutes. So right now I would like to pass the word to my colleague Alex Dugan, who will show a live demo of the example I just covered, as well as an additional one.
Thanks, Roel. So it's also worth to note that VOLTA as a server-based framework is deployed on your internal network. So it's not something we host. Depending on the level of deployment and the use case demand, we could ramp up. So it could be a very light deployment that you could even install like a desktop application on your end, all the way up to us collaborating with your IT in a tiered level, very robust type of web front end. So you're online 24/7, guaranteed. So it can be ramped up to your needs. So I'm going to log into the VOLTA server here. And with MDO, those of you that have done it or know the concept behind it, there's a lot of moving pieces. And these pieces can be data, files, but it even is teams and people. So these are all critical components for a successful MDO. So we saw the need of having a very centralized framework to keep things organized. So VOLTA itself is account-based. So people log in with their credentials. We would link it up, of course, to your company's Active Directory or LDAP systems, so the same credentials as you use to log into your company's workstation or laptop or whatever. We would use that same credentials here. So once you're given a VOLTA account, you have a My File space, and those of you that have used SharePoint or Microsoft, the files, or Google Drive, very similar to that. Anything you upload here is then backed up on the server. So Rule introduced one of the two examples I'll start with, which is going to be our MDO example with the wing design. And with this MDO, I have two disciplines. I've organized it here in my files. We have the OpenVSP piece. So I've uploaded all the necessary files needed for this execution on the Volta server. I can, at this point, version it. So let's say, okay, I want to use an updated version of my solver. I can simply create version. I can drag and drop in the updated executable, let's say. And now all of a sudden I'm on the latest, and my workflow will automatically ingest this if it's configured to do so. I can add comments just to keep track of what's happened. And now you can see I've changed this to V2. And as I mentioned, everyone that I've shared this with, they will either see that I've updated the version, or they will automatically use it depending on how they've configured their execution side. To keep things even more organized, there's metadata tagging as well. So if I wanted to add something, if I'm working on a particular project or an aircraft configuration, I can pick like that, pick the model, what type of propulsion, and so on. So the metadata is very organization specific, and can be configured as such. Once you've had the metadata or attached the metadata to the files, I can quickly search based on that. So if I want to look for this file, for example, I can just type it, see, BSP. It'll look for anything with that. I can add the metadata to filter it down further. So again, I can go by propulsion type, whatever I picked, search. So those of you that have, let's say, shopped on Amazon, the Amazon has millions of items probably, right? But you can easily find what you're looking for. The same principle applies here. As you build up, it gets more and more complex. So that's the My Files environment. Oh, one last thing, the sharing piece, I forgot to mention. So each folder or file you can share with people or groups of people within your organization, and you can give them multiple levels of control or no control at all, let's say, ranging from full all the way up to just viewing. And you can see the other ones in the middle here. The one drawback to the My Files environment is it's very individual dependent. So let's say someone in the organization leaves or transfers maybe to a different team, his Volta account gets deactivated. His work that he didn't share with other people becomes encrypted and basically inaccessible until he is reactivated as a Volta user. So the other environment to stimulate collaboration further is the team environment. And in this environment, there's no individual owner of files, let's say. The team actually owns it. So as long as the team as an entity exists, all those files are accessible. There is a team manager who's appointed as such, and he invites people to join the team and gives them levels of collaboration. And once you're in a team, you can be in many teams. As you saw, I was involved in 3 teams. Anything uploaded in this environment, as I mentioned, is owned by the team. So if I leave, for example, or I transfer to a different team, the files that I put here are still accessible by all the other members within that team. So 2 different ways of collaborating, and both are there to try to get people into the MDO mindset and sharing their work. So once all the pieces are in place for our MDO execution, I need to build the workflows that control the execution, and Rule showed you a little bit of the 2 workflows that we're going to join together here. Currently, the workflow building is taking place within Mode Frontier, and this is the OpenVSP piece. So let's say I'm acting as the aerodynamicist, the aerodynamic subject matter expert. I'm operating within my expertise, within my domain. And OpenVSP is, again, it's a lattice vortex CFD solver, for those of you that don't know. Basically a 2D CFD solver. And I can build my workflow as I wish. again, acting as this subject matter expert. So I identify the inputs that I want to go into the system. In this case, the wing geometry parameters, also an angle of attack parameter that I'm feeding in here, along with any of the necessary support files. So this is kind of getting down into the, the very specifics of each solver. Now, VOLTA and Mode Frontier, these tools are not, let's say, solvers, but they control the execution of the solvers. They kind of are the driver of it. So left to right is the execution order. So first I'm generating the wing geometry, taking in the updated input parameters. Out of that, I may collect some responses. So you can see some of them here. And those responses could be numbers or files. Here I'm exporting an updated geometry file that will be fed into the CFD solver. I'm also exporting an image of my updated wing geometry just from a reference to make sure the wings are looking, the wing shapes are looking as they're supposed to. Once the second process, so once I run the OpenVSP process, I can collect, again, responses from that, which would be the coefficient of drag, coefficient of lift. Finally, attached to those are my objectives or constraints. So these are trying to drive my design in a particular direction to meet all of my objectives and requirements. In this scenario, I'm trying to minimize drag, and I have a subject to a limit on the lift. So I have some type of greater than limit, so make sure that my design is at least has a coefficient of lift of at least 0.2. So once I've debugged this, I'm happy with it. It runs as it's supposed to. I now want to share it with my colleagues. So in the non-server-based MDO domain, I would usually save this to my local drive, or I'd put it on a shared drive somewhere, maybe send an instant message or email to the next guy, which is a structure guy, saying, okay, yeah, I'm done with my piece. Send it to the MDO expert. I'm done with my piece. Here it is. Go and find it. The downside of that is, there's no real control, no version control. It's very difficult to manage, and relying on them to message you, maybe send you files and something like that. So instead, it's much better if I save it to the centralized framework, save it to VOLTA. If I already had built the workflow, I have a choice to update it to a latest version. So if I make a minor change, for example, I could update this workflow, give some comments, send it out, and then those I've shared it with would automatically get notified that this is now the latest version. Likewise, I could open from VOLTA 2. So if I had a previously built workflow that I want to change it a little bit, maybe fix some things, I can come in here, open it from VOLTA, anywhere where I have web access to and a VPN access to your intranet. Once all the pieces are up onto VOLTA, now is the stage to build the MDO. So the way this works is, again, in Mode Frontier, we're going to put the pieces together. I have that OpenVSP piece here. So again, now I'm acting as the MDO expert. I've been monitoring, let's say, I know all the pieces are now in place, or most of the pieces are in place for me to start to integrate these tools together. I can go in, select the project that the subject matter expert has uploaded for me. If there's a stable release, I can tie it to that particular version, or I can say, always give me the latest. So if the aerodynamicist comes back later, uploads a new version or fixes something, I don't have to change anything, because as soon as he uploads it, I'm going to be using the latest version. And another important piece to all of this is that another layer, which is execution layer. And the nice thing is, with VOLTA, it's very easy for us to distribute each discipline to different compute hardware within your network. And it's very flexible. So this compute hardware could be your local laptop or workstation. It could be an HPC. It could be a cloud, or any combination of those. And I can configure it. So I can say I want the aerodynamics execution to go to the Linux workstation, for example, if I wanted to send it out there, or the Windows workstation. This is very organization specific, and this is just how I have it set up as a demo for you to see, but you can clearly envision you'd have an HPC, let's say HPC queue or a cloud queue. I can pick where I want to send this particular piece of the MDO. And VOLTA will handle that distribution. The structural piece, same thing. I'm going down to the next process here. Again, select the project that the structure expert has uploaded for me and shared with me. Again, pick the version you want it to use. In this case, I am using this workflow here, calling Ansys Workbench to do the finite element analysis of the wing. So to make it true MDO, we have possibly some dependencies, some interactions among our disciplines. There's only one interaction here, which is on the lift. So the arrow code is going to output a lift. That lift is going to be fed as an input to my structure, which is going to, of course, increase or decrease the loading on that spar structure. And then finally, after all of that is run, I've attached my objectives and constraints. So as mentioned, we want to minimize the mass. We want to minimize the drag subject to a constraint on lift. So at this stage, I'm ready to go. I can upload this now to VOLTA, save it as a new project, or update an existing one. And then I can come back later, download it. I may want to add in another discipline. Let's say I have a range code I want to add in. I can easily do that. If I go in, find another VOLTA node, VOLTA icon, right? Put it in here. Call this range. The range expert has uploaded his piece, right? So now I can stitch it in, make the connections, upload it, and run it. So you can easily see how this can be, it's modular, so it can easily be appended to or added to as you get more and more refined with your designs. So once this is up on VOLTA, that's kind of the end, which you would need some desktop tools at this stage. The rest is kind of handled and managed by VOLTA itself, so we can jump back to there. This is that workflow that I just showed you, the MDO workflow with the two disciplines. You see it here. Worth noting that there's two levels of execution within VOLTA. The kind of a multi-fidelity approach, you've heard that term, inherently built in to VOLTA itself. So if I had data and I trained surrogate models, we call them RSMs, response surface models. They're basically mathematical predictive models of your system. You can choose to run that. This is very fast running. It'll run thousands of iterations in a matter of seconds. Or I can choose to run the full solver-based MDO. So I have that choice built in. Of course, you can refine it further with logic. So you can go from a 0D code to a 1D code to a 2D code to a full 3D code very easily to ramp up and change fidelities within your workflow. So the power of parameterizing your models, creating these parameterized execution workflows is now you get the choice on how you, levels of how you want to run the model or exercise this model. In VOLTA, you have the choice of doing a single run, which is just you plug in one set of numbers for your design, running it. You have design of experiments, so now you're talking about many different designs in a table that you want to run through. And then we can attach intelligence to it, so an optimization algorithm that can loop and drive your design towards your objective and requirements. So you can really see how you can ramp up from just a single run to now multiple runs, now to intelligent runs. Also, the nice thing with VOLTA is everything is stored and tracked and traced. So every run I've done on this workflow is stored within the VOLTA database. And I can very easily go to a previous run that I've done, change some numbers and run again. So it gives me a nice starting point to start from. So if I pick the last run I did, for example, I can reuse that, that configuration. So this is an optimization configuration. And I've defined the number of variables that I'm operating on. So let's say if I want to take angle of attack out of this optimization, I can simply switch it off, set it to a constant. It's very easy to create different plans of your optimization, different formulations of your optimization, all on the web without ever touching a workstation. Likewise, for objectives and constraints, you can turn them off, turn them on, add new ones, and so on. Constraints. Last piece is, of course, to define the optimization strategy. In Mode Frontier, we offer a vast tool set of algorithms. The same is offered on VOLTA. Many of them are publicly available in the public domain, but also others are proprietary to ESTECO. We offer them to our customers, and we find that the vast majority of our customers end up using one of our proprietary algorithms just because of their advantages. Many of them are one-click, fully autonomous, so you can ramp up, or if you're an optimization expert, let's say, you can really get into the fine details and configure it. I can choose where I want to run this job. So if I want to send it out to a different compute hardware somewhere on the internet here, I can do that. I just pick which one I want to execute on. When I'm ready to go, I can click run. The job will be sent off to the appropriate compute hardware. And once the job's taken, it'll start to say running, and I'll start to receive some data. In the interest of time, I'm going to switch to an existing data set that I've run. And if we go over here, you can see this was run through one of our optimization algorithms called MDO. I have a full data set here of around 100 points. And you can see I've recorded all of my outputs. You can see on the right all the corresponding inputs. So these are all the design configurations. And also I've uploaded that wing image to our database. So all of this data is backed up within the database. I can always come back years later and see what data was generated when and by whom. Of course, looking at numbers is not too interesting. So we want to actually plot on that using that data to get some insights into what's going on. Here's just one example. I've given on the left, I've created a scatter plot. Let me stop this run since it's actually kicking off here, ANSYS. So I've created a scatter plot here of my objectives. So I'm trying to minimize mass, minimize deformation. I can clearly see the Pareto front has formed. One of our charts is shown here. The other one is a carpet plot. Those of you in the aerospace industry probably very familiar with this. Again, another way to represent the dimensionality of this problem. Of course, it is much higher dimensions than that. So we even have a parallel coordinate chart. You can do live, on the fly, on the web, using your tablet or a laptop, anywhere you have internet access. You can do trade-off analyses. So you can say, I want a design that has mass that's below this point, a drag that's below this point. What design am I left with? And the nice thing is on the plots, it'll filter it out and it'll show you which design points are valid for you. If you pick one, for example, Parlop design 133 is interesting. You can even visualize it if you uploaded an image. So you're seeing an image here of one of the other ones. But if I want to see that particular image, I can click on it. I don't think that was the one, but anyway, you can clearly see I can show you the image and it renders right here. So when you come back, let's say years later, you want to see what happened, as I mentioned. There's another piece to this. Whenever you click run, it kind of takes, VOLTA takes like a snapshot of all the pieces as they were at that moment. So it's a nice way to see, what actual files, what versions of the files I was on when this data was generated. A lot of times in this MDO environment, you have data that's, just a few months old, but the information of how that data was generated could have been lost. Drives could have been cleaned or files have been moved. So it's difficult to trace, right? So built within the back end of VOLTA is this tracing capability. So I can clearly see this executable, this version of the executable was used to generate this data. This file was used to generate this data at that time. So I can come back and make sense of it. So I'm going to jump to our second and last example. This one's a little bit more generic for those of you not in aerospace. It's a beam optimization with costing. So just to introduce it real quick, we have going into the 3 disciplines now. We're going to have CAD, which is done by a solver, or CAD package called Creo, PTC Creo. It's going to update the CAD part. We'll have Abacus doing FEA, calculating the displacement and stresses of this I-beam. And we're going to throw in a third tool, which is called a priori, and it's going to calculate the manufacturing cost of these different beam geometries that I'm going to come up with. And based off of that, of course, I'm going to want to try to minimize, let's say, the displacement. So I'm trying to maximize performance of my design, but I also want to minimize the cost of my design. So this performance versus cost is a very common trade-off within MDO. And this is kind of the example I'll put together to show you guys this. And the I-beam you're seeing at the bottom left, that's the kind of the design freedom you're seeing as it's changing the parameters. And on the right, you're kind of seeing the constraints and the applied pressure load on top of the beam. So as the MDO expert, the idea is I want to come in and grab the latest models from the CAD expert, the FEA expert, the costing expert. I'm going to stitch it together in workflow, and eventually we're going to get the apply our objective constraints and get a best design that we can use. So very similarly, it's going to look like this. If I switch back to Mode Frontier, here you can see the 3 disciplines represented by the 3 circles, Creo, Abacus, a priori. As before in the wing example, in the back end of this is another workflow, and the workflow is calling Creo in the background, Abacus in the background, a priori in the background. For a priori to work, it needs an updated native CAD part. So Creo is going to output that for us as a file. VOLTA is going to take care of the transfer. If I'm running distributed on the internet, right, this transfer will be handled by VOLTA via the web. So again, if you have one piece running in a different part of the country or a different part of the world, for example, VOLTA will handle the file transfer from one location to another. Again, very similar setup. Inputs go to our solvers. We extract output and apply our objective and constraints. I've created this already. I've uploaded it to the web. So if we jump back, my files, beam example, that same exact workflow that I just showed you is here. I can see all of my executions I've done on it, again, as it's tracked. One is actually currently running at the moment. So I can click on that. Gives you a nice dashboard of the current run. So where am I out of my requested number of executions? So I've requested 200 different beam designs to come through the optimization loop. So you can see at the moment I'm at around half that. The green ones are feasibles. So I've met all of my requirements. All of my constraints have been met. The orange ones mean at least one of my requirements have not been met. So there's a violation there. Red means there was some failure. So this is common in optimization. Failures do occur. Could be solver failures. Could just be model failures. Like if a geometry is not possible to build, the CAD package may not output anything, and that would be a failure recorded in VOLTA. Many of the optimization algorithms that we use are robust to that, so they can handle failures, learn from them, and learn to avoid them. And consequently, the setup is quite robust. The CAD is simple. So there's not too many errors involved. Only one out of the 90, or actually one out of the more than 100 that have gone through. Looking at the dependencies, I can see again all the moving pieces that were involved here. A few more files than before with the arrow example, but the principle still holds. I can see what version of each workflow, what version of each file I'm using as part of this MDO. Also, the really nice thing is if you really get down, you can also debug on the web too. So we store all of the logs of all the solvers. And if a failure did occur, I can trace it back. I can see exactly what failed and when it failed. So here it's saying Creo failed for some reason. If Creo had some output files or logs, I can quickly take a look at those logs and maybe see, okay, maybe there was a build failure or a regen failure that caused this problem. So once you're at this stage, you're collecting data. You now have the ability to, again, post-process it. So if we go to our results page, go back to the Volta Advisor. I'll start off with something blank to show you how to create these charts. If you have multiple data sets, you can also bring those in as well. Again, multiple runs, you can bring them in. So I think I had a pilot run done on this beam example, so I'll pull that in real quick. This one. It's quite handy to compare data sets if I can bring in multiple ones. So at this stage, I'm ready to start creating my charts. In Volta, we have a rich library of all web-based, pure web-based charts. There's no plugins that you need to download or anything like that. As long as you have a near up-to-date browser, it's Chrome, Firefox, Edge, you'll be able to create these plots right away once you're logged into Volta. So they range from the simple ones, the scatters, 3D scatters, surfaces, some statistical charts. So if you're trying to get information out of the sensitivities, let's say, you can do that here. You can track the performance history, especially useful if you have single objective. You can just make sure that your the optimization is driving you in the right direction. So we can quickly take a look maybe at the scatter bubble to see how this looks like. So maybe I only want to see the best design, so I can filter out all of the non-Pareto or non-optimal solutions. I can apply my axes. So here we go. I'll put displacement on Y. Size, I'll put color. Sorry, size, I'll put, let's say, stress. And then on color, I'll leave blank. And here's your Pareto front that formed. I can add another data set, let's say MIGO, if I want to do a comparison of the two algorithms. I probably want to filter out based on that one as well. So let me filter out on PyLop so you can see only the best of both. So I got both of these optimization runs on the same plot. The kind of the orange circles, that comes from PyLop. The blue circles come from MIGO. Both did a very good job. MIGO hasn't finished running yet, so that's why you're seeing a little bit fewer results. But both did a very good job at populating the trade-off space. I can click on a point again if I'm interested in it. So MIGO point number 8. I can add in our image widget just to take a look at what that beam looked like. So again, I'll pick MIGO point 8, and I'll get a little bit idea of the shape of the beam. So this looks like a very conservative structural beam. You can see the shape of it here that it came up with. If I wanted to look at something maybe a little bit less performance but better on cost, maybe let's pick a PyLop one, PyLop 80. I can add another image. So one more performance, a little bit higher stress. The other higher stress, higher cost. One a little bit less performance, lower cost, a little bit higher stress too. Yeah, good idea of that. You can add more and more plots. If you wanted to do again the parallel coordinate chart, commonly used one to do some trade-off as well. Pick the data set that you wanted to use. So if cost is your most important objective, filter it out, see where you are on the plots. Another nice thing, this is meant to collaborate. So I can create these plots as I like them and share with other people. So if I save this study, I can save it to a team environment if I want it to be seen by a team, or I can save it directly to my files environment. Once it's there, it becomes just another object, just like a file that I showed you how to share files. Same principle applies. If I go back to my files, my study is saved here, when I just did just now. I can share it with others if they haven't shared it or haven't been given permission yet to view this folder. I can add the person here, give them view permission so they can at least open it up, manipulate the charts and the plots. Maybe they prefer to sacrifice a little on cost for more performance. They can change the filters around, save it again, so I can collaborate with my team members. Going a little bit deeper on the run piece, me as a full user, I can run and you know, I can see everything that everyone has done that people have shared with me. I cannot see runs that people have not given me permission to at least see. So the nice thing is all of this, again, is tracked within the database, so I can browse it. There can be thousands, hundreds of thousands of runs here. I'm just looking at some of the you know, the top 100 latest runs that I've done that other users within my organization have done. So again, it's very useful to keep organized, use the metadata, use the tagging. You can quickly find your session of interest, right? So if I wanted to find data that was created on one of my particular product lines, I can just search for a session and then filter it down further to one of my configurations, let's say. Maybe I'll pick a platform. And I could search, quickly find the data that was generated. Now, the piece I kind of glossed over was the execution layer that happened underneath. Since we have a little bit of time left, I want to leave about 10 minutes for questions, but I can show you kind of what that looks like. There's a client process that we require to at least be run on these designated execution machines. And these machines can, like I mentioned earlier, can be a laptop, workstation, an HPC, or a cloud environment. It's running here in the background on this machine. So if I open it up, this evaluator is somewhat automatically configured once you download it. So it knows how to connect to the Volta server, the centralized Volta server, and you have to tell it, you know, what processes it can run. Again, as an MDO orchestrator or framework, there's a lot of pieces. Again, a lot of those pieces are processes or solvers, and within the organization, not all software can be installed on one machine, and one machine can do everything. So in this machine, I have, for example, Excel installed. So I say, okay, this machine can accept Excel jobs. I've installed ANSYS on this machine, so it can take ANSYS jobs. If I didn't have a software installed, I could simply turn it off. And now Volta knows if someone runs this job, it includes a workbench node. That piece of the workflow should not go to this machine. So it's going to do round robin logic to the next available machine that I have permission to execute on that has a workbench installed. It'll automatically get sent to that machine for me. I don't have to worry about it. You can also ramp up based on the machine performance. So this machine is quite powerful. I said, okay, it can take 200 concurrent jobs. If I just had my laptop, I mean, probably want to use much less than that, maybe only accept 4 concurrent jobs. And once you have all of this infrastructure on the back end configured within your organization, it really lets you run in parallel and really maximize that compute hardware. So you can imagine you could have tens to hundreds of people running at the same time, tens to hundreds of thousands of different machines connected, ready to go. So Volta kind of takes care of the load balancing, the parallelization of these runs. If I exceed the compute hardware, it queues it up for me. If compute hardware dies, the job automatically gets re-injected back to a healthy live machine. Or if I add compute hardware to an ongoing run, it's adaptive. So as soon as that compute hardware comes up online, it's going to be used as a worker immediately if there are jobs ready to go. The idea is to keep everything robust, avoid these pitfalls of MDO that are caused simply by hardware failure. A lot of times you run something overnight, over the weekend, and you come back and the machine rebooted or something, and it stopped the run after a few design points. I've lost a lot of time. So with Volta, that doesn't happen as long as you have a robust framework in the back end with redundant machines ready to take the jobs. So at this point, I'd like to open the webinar for a Q&A.
Yeah, thank you, Alex. As I mentioned earlier, if you have a question, you can use the Q&A chat box to type it in there, and we will read it out and answer it. I have a question here, Alex. If you select a queue, say Linux, but you have an executable that can only run in Windows, how does Volta handle that situation?
Very good question. So the best way to handle it would be to have somewhat OS-independent workflows. I know that's not always possible. Here's just one example within our, we call it easy driver integration. So this is integration into a third-party code via some command line. We have built in OS-specific scripts. So if I have a Windows script here and I have a Unix script also here, when you run the job and it goes to Linux machine or a Linux environment, it will automatically use the appropriate Linux code. If that goes to a Windows machine, it would automatically use the appropriate Windows code. That's one approach. The other approach is to split up the queues. So you have a all Windows queue or all Linux queue, and then you would directly specify within your workflow which piece goes where. So it's very flexible for you to kind of control this distribution.
Okay, thanks, Alex. Another question. Can Volta integrate with a company's Active Directory or an LDAP?
Yes, certainly. So you would log in with the exact same credentials as you would any of your other work machines. The point is that we abide by all security standards of the organization, so we don't store any passwords or any usernames, let's say. As soon as you type it in, you say submit, we just query the server, the Active Directory or LDAP server, and it tells us a yes or no. Are you authenticated? If yes, you're let in. If no, you see login failure.
Okay, I got some more questions coming in. Where is all the data that Volta generates stored? On the machines that do the actual executable work, or on the server, or both? Do you have cleanup capability through Volta itself to clear all data if memory is filling up?
It is both. The execution, of course, all the execution files are sent to a machine. The machine executes it. So those files are there. Volta can clean up after itself, and each one of these engines are configured that way. If I go to one of the compute hardware engines, there's a setting here that says, should I clean up or keep all files? So most likely, these files are not traced or stored unless I send them back to the Volta server. So usually the big files, the mesh files, stuff I really don't need, I probably want to clean those up so I can tell Volta, okay, delete all of those files after the execution is done. Files that I want backed up, I can tell Volta to upload those and store them within the Volta server file system and also in the Volta database. So the actual important data should go to the Volta database. So this is a SQL database or an Oracle database. We support many different databases. And that database is much more robust. So if I leave the files on a worker somewhere within the organization, I have no guarantee that that machine is going to stay healthy or alive for any duration. So unimportant files stay there. Important files get uploaded to Volta. And those are very reliable in the database, maintained by IT. So you can always find them whenever you need them.
Okay, we have time for a few more questions. Can RSM equations be exported or copied in such a way that they can be shared via third-party apps such as Excel?
Yes, certainly. That's always part of Mode Frontier. Also in VOLTA, you can do the same thing. As you may have noticed in that aerospace, I did have had both models, RSM-based and solver-based. So the RSMs I can certainly download, share with other people. Again, same thing can be done within a Mode Frontier. The nice thing with Mode Frontier is I can take in the RSMs directly into the Mode Frontier environment. So if I open a file from VOLTA, and it'll automatically tell me if it has RSMs associated with it. If it does, I can say, yes, bring it down. So it'll open it, it'll load it with all of my RSMs already here. And then at this stage, if I expand this out, I can export this as an Excel sheet and share with others. At that point, it's actually license free from us. You don't require any licensing. It's just a standalone Excel workbook that has the RSM model built in as a macro. It can also be exported in a number of different formats. I just quickly glossed over that. Could be SMU. We support MEX, so MATLAB, C code. Could be compiled. Also, I think Java was there and so on.
Okay, thanks, Alex. If you still want to show more of this question, otherwise we have, yeah, I guess here you have the export to Excel example.
Correct. Yep.
Okay, we have time for 2 more questions. First one, can we connect to a cloud compute infrastructure such as AWS or Azure through VOLTA?
Yes, you can. We've had many customers do that. It's quite easy to do. This VOLTA Player process can be run kind of as a clean install. It's just a package that you would deploy. We have Linux, Windows, and Mac support. So no matter what type of virtual machine that you deploy within AWS, you can configure it to, when you deploy it, automatically have the VOLTA Player there, automatically configured, and you fire it up. The nice thing is once you have one machine configured on the AWS or Azure, you can basically multiply it. Very quick to ramp up or scale down as needed. So at one stage, you may configure one AWS machine. Okay, now I want 10. I just say multiply that by 10. Now I have 10 machines. They fire up, automatic connect to VOLTA, ready to accept jobs.
Okay, final question. In the interest of time, I hope you can summarize this a bit, Alex, regarding installation options. What options do we have, and what components from an IT perspective are required?
Good question. For POC deployment, just to get started, we can send you a full package that has everything. So it's a simple double-click install run. That's not very reliable, of course. That's more for POC. So then we can scale it up to maybe a virtual machine that has 2 pieces. We have a piece that does the application server, so that hosts our Wildfly application server, and then VOLTA is installed there. And the other piece is a database piece, and that would be a SQL database most likely. So there's 2 minimum pieces there. Then we can ramp it up to tiered level. So now the database has many redundancies. The application server has many redundancies. We have failover built in. So if one piece goes down, the end user sees basically no downtime at all. It automatically reroutes to a live machine that's healthy. The latter being more IT involved, the former being just you can do it yourself.
Okay, thank you, Alex. I think we've reached the end of the webinar today. I would like to thank again all the attendees for joining us today. If you have any further questions, you can email those to support@esteco.com. And then finally, I wanted to also inform you that in exactly 2 weeks from now, April 29, at the same time, we're going to have our final session on this series of webinars. And there we will cover the topic of democratization in the optimization process, also using our VOLTA framework. We will send the information and the registration links out once we get closer to that date. So for now, I would like to thank my co-organizers and co-presenters, and I wish you a pleasant afternoon. Thank you.